Alright, so let's look at calculation of magnetic moment. So in this video we're going to talk about how we can actually calculate the magnetic moment of complexes. So we're also going to see some other examples and questions as well, like we're going to solve this exercise. So let's start. So basically electrons are found in shells, right? So they spin about their own axis and orbit around the nucleus. So you can think of it as this. So we have the nucleus at the middle. So we have the electrons. The electrons, they spin about the axis, right? So they spin about the axis and they orbit around the nucleus also. So basically this spin movement generates what we call spin angular momentum, and this orbital movement generates the orbital angular momentum. So this is this and orbital angular momentum. So to calculate the spin only magnetic moment of a metal, let's say okay, this is actually the formula we use, n into bracket n plus 2, where n is the number of unpaired electrons, right? Unpaired electrons. So this is us equals to like the spin only magnetic moment. So let's look at this example. So if the number of unpaired electrons for a metal is 1, right? So calculate the spin only magnetic moment. Calculate the spin only magnetic moment. So spin only magnetic moment is n into bracket n plus 2. So the number of unpaired electrons is 1. So we have this to be 1 into bracket 1 plus 2. So therefore we have this to be 3. So the spin only magnetic moment is 1.73 Bohr magneton. Alright, so we'll be able to see that we'll be able to see how to calculate spin only magnetic moment, right? So we also have effective magnetic moment, which is represented as this. So when there is orbital contributions, experimental moment is always slightly higher than spin calculated, right? So we can think of it like this. Effective magnetic moment is always greater than spin magnetic moment when there is orbital contribution, right? And we can also think of the it like this: effective equals to u spin dot orbital contributions, right? So when we have orbital contribution, there's orbital contribution when the electrons end in T2G, or when it ends in T2, like in tetrahedral. So this is for octahedral, right? So for orbital contribution to occur, the last electron in the atom's configuration must be placed in T2G or this. So EG, when electron is in EG, it does not bring about orbital contribution. So let's say octahedral I spin, right? I spin octahedral, we have it to be this. So let's say it's this, and we have this to be this 3. So T2G, and this is EG. So for D1, it occupies this. So there's orbital contribution because the last electron is on T2G orbital. So for D2, there's orbital contribution. Now looking at D3, D3 is still on T2G, right? But this T2G is now completely filled. So when T2G is halfly or fully filled, right? When it's halfly or fully filled, no orbital contribution. There's no orbital contribution, right? So let's look at D4. D4 is this, right? It's on EG, so no orbital contribution. D5, no orbital contribution. So D6 is back to T2G. So there's orbital contribution in D6. In D7, there's orbital contribution. In D8, no orbital contribution. In D9, no. In D10, no orbital contribution. So for tetrahedral also, tetrahedral is always I spin, right? So that is basically this 3, and this is 2. So this we have E and T2. So for D1, no orbital contribution. D2, no orbital contribution. D3, yeah, there's orbital contribution. D4, there's orbital contribution. D5, no orbital contribution. D6, no orbital contribution. D7, no orbital contribution. D8, there is orbital contribution. D9, there's orbital contribution. D10, no orbital contribution, right? So another way to check whether there is going to be orbital contribution, we've already explained that in the first point there. So, but look at it, orbital contribution from octahedral T2G orbital is also possible only when the electrons are in this 1, 2, 3, 4, right? That is when the T2G is not completely or partially filled. So we said the other time that this is octahedral, right? And this is T2G, this is EG. So we said 1, yeah, orbital contribution is possible. So D2 orbital contribution. So D3, no orbital contribution. So let's look at D4, no orbital contribution. Let's look at D5, no orbital contribution. They are all on EG. So now let's look at D6. Yeah, D6, there's orbital contribution. Now let's look at D7. D7, there's orbital contribution. Please ignore this red point here. So D7, there's orbital contribution. D8, no orbital contribution. This is completely filled. So D9, no orbital contribution because it's on EG. And D10, no orbital contribution because it's on EG as well, and it's completely filled, right? So for tetrahedral also you can do the same. Tetrahedral is this, we have it to be this. So this is E and this is T2. So D1, yeah, there's let's write it here, tet. So D1, it's wrong. So D2, it's out. D2 is out also. So D3, yeah, it's possible. So D3 is possible. So D4 is also possible. And D5 is out. So D6 is out. So D7 is also out. So D8 is possible. D9 is possible, and D10 is out as well, right? So now let's look at this question. Compare the spin-only magnetic moment for a I octahedral and tetrahedral D7. So basically, spin-only magnetic moment is root n into bracket n plus 2, where n is number of unpaired electrons, right? So basically, let's draw the structure for octahedral. So let's put tetrahedral here rather. Let's put tetrahedral. We have this to be this. So this is E and this is T2. So for this we have it to be this and 3 here, right? So this is T2G and this is EG. So D7 is going to be 1, 2, 3, 4, 5, 6, 7, right? So for this, remember they are all I spin. So it's going to be 1, 2, 3, 4, 5, 6, 7. So the first thing now, let's look at this. The number of unpaired electrons is 3 for the 2. So looking at this formula, we might want to say that they should have the same spin-only magnetic moment. So the spin-only magnetic moment ordinarily should have been 2 into bracket 2 plus 2, right? And that should have given roots. This is 8, and that should definitely give us sorry, this is 3, this is 3, and this is 3. So basically this should give us 15, right? So we expect this to be 15, and so root 15 is going to be 3.87, right? So bore magneton. So we expect the two should have the same spin magnetic moment, right? But in the actual sense, when you do this experiment in the lab from experimental data, you would always observe that this octahedral would have a higher effective, like the real value itself is the effective. So you expect that the effective for octahedral to be higher than the value for tetrahedral. And why is that? Looking at this, we see that in this case the last electron was on the E orbital, right? The E. So there is no orbital contribution here. The orbital contribution here is quenched, right? But looking at this, the last electron 1, 2, 3, 4, 5, 6, 7. The last electron is here, so it's on T2G, right? And it brings about orbital contribution. So you expect that the U effective for this one to be greater than u spin, right? To be greater than u spin, and yeah, to be greater than the u spin. So the u effective for this one will definitely be greater than 3.87, right? Alright, so having said that, when there is orbital contribution, the effective spin will be greater than the spin only magnetic moment. So, and recall that experimental moment, which is also this, is slightly higher than this, calculated due to orbital contribution. So also recall that for a high spin octahedral and tetrahedral D7, the octahedral has magnetic moment higher than this one due to orbital contribution. Now it's important to note that D7 complex for tetrahedral, like this, it's important to note that D7 complex for tetrahedral also has higher magnetic moment than 3.87. So look at it. For D7 tetrahedral and D7 octahedral, right? So we say that there was orbital contribution in the case of octahedral. So we expect that the U effective to be greater than U spin, right? So because this one there's no orbital contribution, we do not expect that the U spin, we do not expect that the U effective to be greater than U spin. We do not expect that. But in the actual sense, we saw that after experiment, it was shown that this 7 tetrahedral also has higher magnetic moment, higher than this, although it is smaller than that observed in the D7 spin. So now, what is actually responsible for this? So let's look at this question here. So looking at this, why is it high despite the fact that orbital contribution is quenched? So this leads us to the concept of spin orbit coupling. So spin orbit coupling is usually the most common reason for that. It opposes the quenching of orbital contribution. Recall that we say that in the question that what is responsible for the high magnetic moment of D7 tetrahedral complexes despite having their last electrons in the E orbital quenched. So this is mainly spin orbit coupling. So as a result of spin orbit coupling, we have a modification to the spin only formula. So now we have this to be U effective equals to U spin and an addition, which is the spin orbit coupling. So this is 1 minus alpha this and this. So we have this. So it's the same thing as root n into bracket n plus 2 and 1 minus alpha lambda and change in octahedral splitting energy. So basically you need to note this, that this will be given in your questions, will always be given. All complexes have their octahedral splitting energy value, so it will always be given. So this also for the complex, let's say for Cu2 plus any of the metal ion, it will always be given. They have their value for this lambda. So but now for this one, it's here. So this alpha value is 4 for a grand term and alpha is 2 for E grand term. So recall that we from term symbol we're able to like deduce the grand term. So let's say for a given term symbol, let's say it was S10, right? So S10, this is not A, this is not E. Now this brings us to the concept of spin orbit coupling again. So basically in the concept of spin orbit coupling, we have the s orbital split to what? It splits to A1G, right? So p orbital splits to T1G, right? So d orbital, let's demarcate them. So d orbital splits to Eg plus T2G, right? So f orbital splits to A2G plus T1G plus T2G. So please and please, you need to know this. So spin orbit coupling, s orbital splits to A1G. P, I'm writing it again for you to like memorize it. So P splits to T1G, D splits to EG and T2G, and F splits to A2G, T1G and T2G, right? So now let's look at this exercise. So calculate the value of effective magnetic moment for this complex and comment on the difference in its this and this value. So the first thing you need to do is to calculate the oxidation number of nickel in this complex. So basically nickel En3 2 plus, we have it to be Ni plus 0, because this a molecule, so we have 3, so we have plus 2, right? So we have Ni equals to plus 2. So the oxidation number of nickel there is plus 2. But now let's look at the configuration. So Ni is basically 28, right? So that's 4s2 3d8. So now for this, we're going to have it to be Ar, right? So 4s is losing 2 electrons, so it's going to be 0, and then 3d8. So we have the configuration to be this, right? So the next thing now we need to do is to calculate the U effective. But before we calculate the U effective formula is this, right? We have it to be root n into bracket n plus 2, and then we have 1 minus alpha wavelength over this value, right? So this value has been given here, this value has been given here. So now we need to know this A value, and we also need to know the number of unpaired electrons. So we need to know A value, and we need to know the number of unpaired electrons. So we get this from the grand term symbol. So now let's draw this. So we have this is energy. So we have 1 2 3 4 5, right? So and it's splitting. No, this is octahedral. This is a bidentate giving 6 ligand. So this is octahedral, and it's going to split to T2G and EJ, right? So we have this, and we have this 2 3. So T2G, and we have EG. So this is 8 electrons. So it's going to be 1 2 3 4 5 6 7 8, right? So the 8 electron feels this way 1. So looking at this, this is going to give us a high spin configuration. So it's going to be 2 3 4 5 6 7 8, right? So it's giving us this configuration. So now the next thing we need to do, the number of unpaired electron is 2, right? So we can say that the U spin here is basically n into bracket n plus 2. So we have it to be root of 2 into bracket 2 plus 2, and therefore we have this to be root 8. So root 8 is basically 2.828. So this is the value of root 8, right? So and this is the spin only magnetic moment for this. Now we need to also get this arc pair of spin orbit coupling so that we can get the total value. So basically we need to find the grand term. So first thing you need to do, calculate the number of unpaired electrons, which we've done. The next thing is to calculate the grand term. Calculate grand term. So let's see the grand term. So recall that we said term symbol is always 2s plus 1 and j. So in this case we are not going to really need j value, but we need this and this, right? So let's calculate the spin. So the spin is basically the summation of m s. So we have this to be plus 2 plus 1, 0 minus 1 minus 2, and this one half and negative. So this one will basically give us 0, spin of 0, spin of 0. This one will be plus 1 over 2 plus 1 over 2. So this will definitely have plus 1 over 2 plus 1 over 2, and this will give us 1, right? So we can therefore say that this part is going to be 2, 1, and then we have plus 1. So that is going to give us 3. So the spin, the multiplicity is 3, right? So now let's calculate the L value. So L value is simply the summation of the ML, and these are the ML, right? So these are the ML value. So we're going to have 2 electrons times 2, we're going to have 4, plus 2 electrons times 1, we're going to have 2. This one is going to give 0, and this one will give us minus 1. This one will give us minus 2. So we're going to have, this one cancels this, right? So we're going to have 3. So looking at the table, L and energy level. So this is energy level. So when it's 0, it is S. When this is 1, it is P. When it is 2, it is D. So when it is 3, it is F. So basically this is F, right? So we have the ground term to be F, and the top part is 3, right? So let's neglect the J. So now recall that we said the F orbital, the F term will split to A2G plus T1G plus T2G, right? So this ground term will therefore become 3 A2G. Let's put it here. So 3 A2G, so let's write the ground term again. So we have 3F will become 3 A2G plus 3 T1G plus 3 T2G. So now we've gotten that. So the next thing we need to do is to calculate this value. So this becomes 1 minus. Now looking at the alpha is going to be this. Let's look at the table for alpha. So we have it from here that alpha is 4 when the ground term is A, right? So the alpha is 4 when the ground term is A. So looking at this here, so this is the ground term here. Assuming in the case of, let's say in the case of, we said S will give us A1G, we said P will give us T1G, D will give us EG plus T2G, and F will give us this here. So in the case of this, the alpha will be 4. In the case of this, there's no alpha there. There's no alpha there. It's going to be 0 because it's no, we don't have for A or for E. A is 4, E is 2, right? So this one, in this case, it will be 2 because we're only dealing with this. But in this case, alpha is going to be 4. So we're going to have this to be 1 minus, that's going to be 4. So the value for this, in the question, we have this to be negative 315 per centimeter. So erase some part of the board. So we're going to have this to be the term symbol is 3F, right? So it splits to 3 A2G plus 3 T1G plus 3 T2G, right? So we have this calculation, this one 1 minus alpha wavelength over octahedral, right? So the next thing is that we have 1 minus, so the alpha is 4 from A, alpha is 4, so we have to be 4, and the wavelength is minus 315 over, so the next thing is this 11500. So this it's important to know that this denominator here is only for this part, not for the whole stuff there. So basically what we're going to have is we're going to have 1 plus 0.110. So now recall that U effective equals to U spin times this 1 alpha n and this. So we're going to have this to be the U spin was 2.828 times 1.110. So everything will give 3.14, right? So this is the answer for the U effective. So now comment on the difference between this and this. So since the configuration gave a orbital coupling, orbital contribution, right? You know, this is D8, right? And when we did the configuration, we add this, so there was orbital contribution 7, and so this is 5, this is 6, 7, and this is 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. So okay, there was no orbital contribution, basically no orbital contribution, right? But the value for U effective was still greater than U spin. So this was due to basically spin orbit coupling. So assuming there was orbital contribution here, it could have been higher, and the reason could have been orbital contribution. But because despite the fact that there was no orbital contribution, the U effective was still greater than the U spin. So the reason is basically spin orbit coupling. So looking at this question also, at room temperature, the observed U effective was 4.75, right? So is the complex high spin or low spin? So basically, for us to do this, we need to calculate the oxidation number. That's the first thing. So, and for us to calculate that, we simply bring the complex to be Cr plus 3 into bracket 0 plus 2 into bracket minus 1. Bromine is an halogen, so that's oxidation number of minus 1 equals to 0. So Cr equals to this becomes minus 2 and brings, so it becomes plus 2. So chromium is basically argon 4s1 3d5, right? You know, this is an exemption. So but Cr2 plus therefore becomes Ar 4s0 and then 3d4, right? So now looking at this, at room temperature, the observed value for U effective for this complex, is it high spin or low spin? So let's look at it. We don't know if it's high spin or low spin. 1, 2, 3, 4, 5. So this is octahedral. We know that it's octahedral. So we're going to draw this in this configuration. So we have this. So D4, that's going to be 1, 2, 3, 4. So it's going to be 1, 2, 3. So let's call this I spin. Let's call this I spin. So this is going to be D4. For low spin is going to be this, right? Low spin is going to be this. So that's going to be T2G, EG, right? It's going to be 1, 2, 3, 4, right? So the number of unpaired electrons here is 4. The number of unpaired electrons here is 2. So now let's calculate the spin. So the spin here is basically root n into bracket n plus 2. So we have this to be root of 4 into bracket 4 plus 2, and we have it to be root 24. So this is root 24, and for this is going to be 2 into bracket 2 plus 2. So we have this to be root 8. So basically root 8 is 2.828, but root 24 is this is 4.89, right? So this is 4.89 and this is 2.84. So we can clearly see that this one is closer to this. That's one. Also looking at this, no orbital contribution here, well, there's orbital contribution here, but regardless, this was closer to the observed U effective value. So this is basically the answer. So I spins, basically I spin. So here is it. The value of the spin is close to the observed value and is consistent with the I spin complex.